Welcome to our lectures on the advanced power electronics and control. Today we will continue with the PWM rectifier and the power factor improvement technique. We were discussing basically the control current waveform for the CPM mode. Same we shall continue in our coming class. Essentially, these are the frequency response, So, what happened, this is the basically the sinusoidal waveform, and this value is basically a modulated index is something of the slope, and R base is 12 by Ts, and the peak value is basically Ig by, it is a normalized value. So, what happened, you can see that when actually this I base value R become 2 I base, then actually distortion comes, and distortion will be lower if this actually we have RE equal to 0.1 R base, and this is the actual sinusoidal. So, more and more actually the current waveform will be peaky if this RE is more than R base. So, we can meet harmonic limits if the range of the operating point is not too large. So, if it is actually huge variations of the load current, that is from R equal to 10 R base to 1 R base, that is what we have seen in this waveform, then what will happen, this in this range. So, we may not actually have a control over the THD of the desired THD. So, we can have a control over the THD with a short range of time. So, accordingly it will be designed, and thus what happen when it has a distortion, though we cannot control the harmonic content of the system. So, difficult to meet the harmonic limits in a universal input supply. This is one of the biggest disadvantage of this boost type power factor corrections, where you can for the fixed load it is very well designed, but if you have a very huge variation of the load, so it may be have a problems of the distortions. Now, to overcome this, we can think of some hysteresis controller. So, that is a, but what happened, till now you had a constant switching frequency and all those things. So, your switch you can choose a particular switch choosing on the particular frequency. Moreover, your design of the boost inductor become easy, that actually this is your switching frequency. Once you go for this hysteresis control, your switching frequency is not fixed, but you can have some added advantage, but it is limited by the some percentage of it. So, you can approximate it like that, and thus what happened, you got a hysteresis control. This is a hysteresis control. What happened, you have this Vg, which is basically nothing, you have Vg after rectification, you got a ripple kind of voltage, thereafter you have a boost topology. There you generate a envelope, hysteresis envelope, which can be generated by a single op amp, positive or negative band, and you can keep the current within a positive and negative band. So, you can have a different kind of band. This is called actually constant band. You can have some band is something like this, it is called proportional band, 1% band, because here it will be 0 and here it will be more, and ultimately then you can see that actually here current required to be frequency is very high, here frequency is quite low, and also here you can see that here frequency, if you keep it like this, you can see that frequency here is low and here it is high. So, you do not have a constant frequency operation, and you can have this kind of operation, that is called proportional operation. You can, this is called this is another mode of control. There is a one Fairchild chip that operates in this mode, and UC 3854 operates in this mode. The critical condition mode of a boundary between the CCM is actually this what happen, you know, you will allow the current to grow according to the your voltage limit. So, you will have a voltage envelope. So, and you will give a some DC biasing, so that you can get a minimum current. So, accordingly as this envelope changes, you know, current you allow to go and strike this envelope, and thereafter current will be switching on. And a petal type of waveform you may get, and you may have a interleaf boost converter, there is a inter between another array, they can superimpose it and almost you get a sinusoidal waveform. So, this is the way of implementations of hysteresis control. Since you have high frequency switching and you have a EMI EMC filter, generally it suppresses the conducted noise, and you have VG that is of this pattern. Thereafter you sense it, thereafter you have multiplied, you have a kg, and you have a same thing. What happened, you know, you got a IG zero crossing detector. So, it will actually fit it here, and ultimately current you will be allowed to ramp on till actually it touches this envelope. So, it has an envelope. So, once it touches that envelope, that will be reset, again current will come back. Then again actually once current touches 0, then only again it will be reset and current will be allowed to ramp on till it is actually touches the envelope in this pattern or this pattern. This is the way of operation of the critical conduction mode control. So, what is the advantage of it? There is a pros and cons of this. Actually, the first take the advantage, rather simple and then low cost IC. So, it just required to sense the VGT, that is the rectified rippled voltage, and accordingly when it touches this actually upper envelope, switch will be off. Low frequency harmonics are small with constant transistor on time for the boost converter, and size of the inductor will be less because it can operate in the discontinuous conduction mode, because there you can find that in a continuous conduction mode control is quite difficult. But disadvantage is this, basically it increases the peak current and current become peaky, and thus when current become peaky, the biggest disadvantage of it is that you have a problem of EMI EMC. Then thus increased conduction loss and reduced switching loss, require larger input filter to filter it out, variable switching frequency, and smear out the current EMI spectrum cannot be synchronized with the converter switching frequency, and this mismatch actually leads to the radiated noise. So, these are the disadvantage of actually control current mode waveform. Now, we shall ensure that transistor is on for the fixed time T on. So, this is the you have a on time control. Transistor off time when inductor current reaches 0. We have please referred to this actually the model, you know how you reset it and how it will be triggered here. So, the ratio of Vg to Igt is actually Re 12 by T on, and on time is a function of the load power and the average voltage. So, it will be T on will be actually 4 Lp by V square m, and the inductor boost second balance you can do, and from there actually you can calculate that actually if it is around 50%, the T off equal to T on, that equal to Vg equal to minus of this value. Now, solve for how to controller varies the switching frequency over the AC line period. So, Ts equal to T off plus T on. So, Ts you know that this depends on the parameters which has been described here, that is basically average power, power and the average voltage and the value of the inductor. So, you put it like that, ultimately Ts will be Vm square plus, actually it will be a variable since basically Vg varies, Vg is a rippled DC voltage. So, for this reason this term will vary ultimately Ts will vary. So, when you will have a maximum switching frequency, when this value actually close to 1, basically it happens once it at the peak. So, at the peak you will have a large switching frequency or higher switching frequency, and at the 0 crossing you will have a lower switching frequency. So, similarly, for the sinusoidal voltage variation, the switching frequency will be varied as follows: reciprocal of it, that is Vm square by 4 Lp 1 minus Vm by V sin omega t, and from there you can calculate what should be the value of the maximum value of Fs, that is Vm square by 4 Lp, and the minimum value of Fs Vm square by 4 Lp 1 minus Vm by V, and this equation can be used to select the value of the inductance, but depends whether you have a large variation or not. So, if it is very difficult to design inductor, because inductor has to set for its switching frequency, and if it is a wide range of variation, if it is actually it is within a mean value, if it is very 10%, it is fine. But of course, if its frequency varies 1 kilohertz to 2 kilohertz or actually 10 kilohertz to 20 kilohertz, it is very difficult to design those kind of inductor, and then you will find that roll off will be different, because value of the inductance will change according to the switching frequency, please mind that. So, to control the current waveform, we have a following discussions. So, it is essentially a nonlinear control, because switching frequency is variable, and instead of the average current mode control, you have a variable control, and can obtain simple control input waveform without sensing AC input voltage. This is also possible, and with the operation of the in continuous conduction mode. So, you do not require any input in your AC system. Mind you, this same kind of system will work for the single phase system, but we require to change for the 3 phase system, because 3 phase does not have a replica to find it out. So, we require to do some kind of modifications to use it for the 3 phase system. The integral of the sense switch current charge is compared to a nonlinear waveform and a linear lamp, and by a cycle by cycle basis. Carrier waveform depends on the converter topology. So, if you have a boost topology, it will be something else, and if it is a buck topology, it will be something else. Very low harmonic in continuous conduction mode, but waveform get distorted in case of the DCM. So, it is very sensitive to the load. If load changes and your transistor occur DCM to CCM, then you will find that THD is not acceptable to you. Peak current mode control is also possible with different carrier. So, phase shifted different carrier is also possible, so that you have a petals kind of waveform. Another petal may be phase shifted by 30 degree, you may superimpose it, and thus what happen, you get a better THD. So, this is a control of the current waveform. Now, you got a CT, so ultimately you sense this current, and now it has been actually rectified and stored into the capacitor, and of course, you can discharge this capacitor by a switch. So, then this value is fed to the comparator, and what happened, you got this rippled DC, and you can see the petals of it. So, it required to be compared. So, this is the value of IS T, and this is the value of the Vc, and ultimately this will be value of Vi, and this is the way of actually current will increase, and this will be the Ts. So, ultimately again it will be reset for the clock pulse once this actually nonlinear carrier is over, and again capacitor will be discharged after the when it will require to be the reset the flip flop to capture the second cycle. So, average switching current is basically this. We can make the controller to regulate average switch current by integrating it. So, essentially integration can be done by the op amp with the capacitor feedback. Integrating monitored the switch current, resetting the integrator to 0 at beginning of the each time period. See that this is basically the integration part of it. So, it will store the integration of the current and we will reset it at the beginning of the each cycle. Turning off the transistor when integrator reaches the reference value. So, the control actually diagram in the integration as follows. So, Vi should be equal to 1 by C 0 to dt, you have to integrate over it. So, you can get that basically Vi is basically Is by N is the number of turns ratio of the transformer or the CT into Ci into the switching frequency Fs. So, what should be the actually the emulator resistor? Emulator resistor, as you know that it is Re, that is IGTS equal to Vg by Re. So, it will be Vg by Ig equal to dt, that is the duty cycle, into IGTS. Relate the input voltage to the output voltage and we assume that it is a continuous conduction mode, then VGTS equal to d dot into Vt. We have, please recall, in our previous class we have done the actually small signal model. So, from there actually we can relate it. So, substitute the above equation how average switch mode should be controlled is Is equal to dt 1 minus dt Vt by Re V control. So, this way you can control this actually charging of the capacitor and thus the current of the switch. So, to desired control from this previous slide we can rewrite it as Is equal to dt 1 minus dt into this one. From there the control voltage Vc become actually V control T by Ts 1 minus T by Ts for this, and Vc T plus Ts equal to Vct. The controller switches the transistor off when integral voltage actually equal to the carrier waveform and leads to this actually this Vi dTs should be equal to Vc dt, and thus that should be equal to V control dt into 1 minus dt, and we can do a little approximations, and after doing this approximation that this emulator resistor with the control becomes dt 1 minus dt Vt by 1 Vt by Ist by Ts. So, it ultimately it leads to Vt n Ci Fs V control. So, this will be the emulated resistance in case of the current control mode. So, essentially the block diagram become this, you got a V control and you got a actually the current switch and you got a capacitor. Capacitor is required to be reset in every clock pulse. Starting of the clock pulse ultimately it will compare with the Vt. Once actually this results become this becomes a current control and integrator is going to reset by this switch. So, please note that this is a way actually we operate this actually continuous control mode of operation for this converter. So, this is the explanation of this converter. Now, we have discussed for the boost PWM technique and its different way of control. Now, let us, but it is restricted to the single phase supply and thus it is restricted to the low power applications, but in case of the high power applications and the 3-phase system, this kind of system required to be modified, because after rectification, you know, if it is a diode based rectifier, you have a 6 pulse waveform. So, that the 3 phase waveform pattern is missing and you have a constant DC value. And for this reason all the method is required to be changed. Let us see, let us have some analysis now on power factor improvement techniques. So, essentially you know that in power electronics we have a displacement power factor and the actual power factor. Displacement power factor decreases as average value of the output voltage VDC decreases with the increasing the firing angle. Since you are, this is your sinusoidal waveform, you are triggering at an angle alpha, if you increasing the alpha, your displacement power factor is going to be increased and thus you get poor power factor. This is applicable both 3 phase as well as the single phase waveform as well as full waveform, full bridge, half bridge, all kind of thing. There are 3 techniques to improve power factor. We have seen while discussing with the different pulse converter, that is 6 pulse converter, 12 pulse converter, 24 pulse converter, 48 pulse converter. So, we can see one thing, that is a extinction angle control. Generally thyristors can only give you turn on control, turn off control is not possible. So, you require a full control switches like GTBO or IGBT to have a full control switches and to have a extinction control. So, that you can actually, you have a sinusoidal waveform, you can chop here as well as chop here. So, current waveform may be this, but it may have a TST, but it can have a unity power factor. Similarly, you can have another method, that is symmetrical angle control. Third method, that is quite important method, is pulse width modulated PWM control. We shall see all by one. Now, see that extinction angle control. So, what happened in this case? If it is required to be line commutated, you require GTO, otherwise you can have actually a current that can be leading. So, you can do that. So, what happened? You have a sinusoidal voltage and you have actually chopped it before 180 degree, and thus what happened, this actually this is the current through the thyristors and input of this current is given by this, and you can find that the fundamental of this actual input current is basically the leading. Because of this you have chopped at an angle beta. So, this kind of thing is called the extinction angle control. So, this control technique is applied on single phase, full wave, half control, force commutated converter. Either you have to have a force commutated converter or you should have a GTO. Thyristors T1 and T2 are replaced by the self commutated switches, power transistors or its equivalent IGBT, IGCT, GTO. This control switch S1 is turned on at omega t equal to 0 and turn off by the force commutations when omega t equal to pi minus beta. So, the turn on at omega t equal to pi and turn off at 2 pi minus beta. Output voltage is controlled by varying the extinction angle. So, you have a integration will change, and the waveform of the fundamental component of the input current leads the input voltage, and thus, so what happened, displacement power factor is increased, and this technique is useful to simulate the capacitive loading without line voltage drop. So, this is quite actually good applications for it. Now, let us see that what happened to its average value, and we have actually started an angle alpha, now we have an extension angle control, we will actually chopped at an angle beta. So, for this reason the average voltage VDC will be actually you can write 1 by pi 0 to pi minus beta under root Vm sin omega t d omega t root 2 by pi Vm 1. So, you can get, if you do the integrations, effective value will be become actually V plus V cos beta. So, value of VDC is varied from 2 root 2 by pi to 0, as actually this beta varies from 0 to pi. And similarly, you can have the RMS value, that is V 0, you can same way you can integrate over it 2 by 2 pi 0 to pi minus beta 2 V square sin square omega t dt equal to V by 1 by pi pi minus beta plus half sin 2 beta to the power half. So, again you will have a double frequency ripple and all those things. So, this will be the value, and you know V 0 also varies from, you can see that you can choose pi equal to beta, and you know we can have also, if it is pi, then also this value becomes 0. So, similarly this value also can vary from V to 0. Now, another is a symmetrical angle control. So, you will chop from both the sides. So, you chop this side as well as this side. So, what happened here, you have a upper to thyristors, and thyristors can be actually commutated, or you can have a force commutation, or you employ GTO. So, you trigger an angle alpha, and thereafter you actually trigger it off at an angle actually beta. So, you get actually this part of the waveform, and so on it will continue, and we assume that load current to be continuous. So, thus you have IA something like this, and source current will be actually steps, and the fundamental of it will be the sinusoidal one, and you can see that it is at unity power factor. And by changing this actually conduction angle and the extinction angle, you can also change the power factor of it. So, this control technique is applied to the single phase half control force commutated bridge converter as shown in the previous pattern. Thyristor T1, T2 is replaced by the cell commutated devices S1, S2. S1 is turned on at pi minus beta by 2 and turn off at pi plus beta by 2. So, beta should be the angle of conduction. Now, S2 is turned on 3 pi minus beta by 2 to plus 3 pi plus beta by 2. Output voltage is varied by varying the conduction angle beta. Gate signals are generated by comparing half sine wave of the DC signal, and sine wave can generated by using a full wave rectifier, either of it. The gate signal can be generated by comparing the triangular wave with the DC voltage, and fundamental component of the input current is in phase, or you can change if you wish, you can then you have to have a different little change of these values. Input voltage, and thus displacement power factor is unity. So, power factor is here also it is improved. So, we can do the control like this. So, this is the actually the triangular wave, and this is the DC level Vc, the controller voltage. Ultimately, you will have here you will turn it on, and here you will turn it off. So, this angle is beta, and you can change this level accordingly you can get a lower conduction angle, and you can bring it down, you get higher conduction angle. So, average output voltage is same way you can integrate. So, you will find that 2.2 pi Vm sin beta by 2. Similarly, you can calculate the RMS value for for pi minus beta by 2 to plus beta by 2 v square by 2 sin square omega t. Ultimately, you get v by 1 by pi beta plus sin beta. So, this will be the average value, and this will be the average value, and this will be the RMS value for continuous conduction mode. So, for actually symmetrical control, we shall continue to the another method in our next class. Thank you for your attentions.